Right. So, having illustrated how we can derive our normal equations in regression analysis, I think it is time for us to illustrate with an example. Just to save me time, I've already done the calculations of the various components. I'll walk you through these. After I've done that, I'll explain the calculations that you need to do. So now suppose you want to start the relationship between education and wages. You collect a sample of, the sample of about 7 people, and these are their levels of education. Someone who never went to school, and someone who just ended in primary school, someone who ended in grade 11, someone who ended in matric, someone who did undergrad, honors, and masters. And these are their wages. Yesterday we were working with these, with the thousands here. I have rescaled the data, so I have written it like this, but it's in thousands. Okay? We clearly see that as your level of education increases, your wages also increase substantially. This is the mean, this is the sum, this is the mean, sum, the mean. Now, because of rounding off errors, we didn't get exactly 0, but for all intents and purposes, you can see that these numbers are 0, which means if you sum the deviations of a variable from its mean, you should get 0. This is what you see here. And the product of the deviation of wages from their mean and of education from the mean, if summed, gives us this number here. And it is this number that we adjust by degrees of freedom to get the covariance. We did this in our first video. If we square this and then sum that, we get this, and it is this that we adjust with degrees of freedom to get the variance of y. The same applies to x. We adjust this by degrees of freedom to get variance of x. From variance of y and variance of x, taking square roots, we get their respective standard deviations. This particular those other 2 columns, they are just for helping you understand what all the algebra we were doing actually means when I was showing you the various kinds of funny manipulations you can do, or the various kinds of fun you can have manipulating the summation sign. Notice that this product of the deviations will give you the same value as y minus y bar times x. You see that? Same value. Notice that x minus x bar has the same value as x minus x bar times x. We showed this when we were deriving our beta 1. So they give you the same value except for rounding errors here. But so this is just to help you see that what we have here, this can give us the covariance. Okay? So now let's calculate the covariance. Our covariance requires us to divide this number by degrees of freedom. We used this data to calculate the mean. So we have 1, 2, 3, 4, 5, 6, 7 people. We subtract 1. So our covariance is actually 355.86 over 6. And we should get 59.31. It's our covariance. Okay? The variance of y requires us to come under this column. This is the total. Now the variance is equal to this total divided by degrees of freedom, which is 7 minus 1. which is 6. Now I don't have space. Can I just squeeze here? So it's that number divided by 6, and we should get 111.119. So it should be written here 111.119. The standard deviation is the square root of this. So the square root of 111.11 is 10.541. Okay, we are done with that one. Then variance of x, you come under this column, which means you want to say 227.428 divided by 6. The answer you get there should be 37.905, and the standard deviation will be 6.157. Okay, what else is left? We need the correlation. The correlation requires us to divide the covariance by the product of the standard deviation of x and standard deviation of y. So that's 59.31 divided by 6.157 by 10.541. Okay. The answer that you get should be 0.914. We did this yesterday. You can see that this is a highly reliable positive association between education and wages. Now, we now have all the ingredients we need to calculate our coefficients. Now, what you remember from what we did using the covariance variance method, we said our beta 1 is actually equal to covariance of x and y over variance of x. So, covariance of x and y is this, which is 59.31. And you divide that by variance of x, which is that 37.905. Now let me just remove this one for beta note to have space to continue writing. So if you simplify this, you will see that you get something like 1.565. Okay? Now let's try to do using the correlation standard deviations method. Beta 1 is equal to correlation of xy by standard deviation of y over standard deviation of x. This should be equal to, our correlation is here, 0.914 times standard deviation of y is there, which is 10.541 over standard deviation of x, which is 6.157. I can assure you that if you calculate that, you will get this number here, 1.565. You see that? Now, remembering that our data is measured in thousands, actually this number here is actually 1,565. That's the number, because All this is measured in thousands. And all these can be adjusted for the thousands we have there. You add your thousands. Okay, so if you add your 1,000 there, you multiply by 1,000, multiply by 1,000, all of them will be adjusted, okay? But you don't have to worry about that. I'm just saying once you get the final answer, remember that it is in thousands. Okay, when you interpret it, you should know that it's in thousands. This is not 157. It's actually 1,565 rands. Okay, now how do we get our beta hat naught? Our beta hat naught is y bar minus beta hat 1 x bar. Okay, our y bar is this number here, which is 13.071 minus our beta there, which is 1.565 times our x bar, which is 11.29. You can simplify that. Let's just check very quickly. 13.071 minus 1.565 times 11.29. Right, so what you get is minus 4.598. So which means if you were to come and write, can I clear this part here? I want to maintain the table as it is. If you were to write your regression, which was y is equal to beta hat naught plus beta hat 1x plus this, okay? Now because this has to be estimated by the difference, you can remove it there and put your estimates. You have minus 4.598 plus 1.565x. This is your regression line. When you fit this line to the data, it is the line of best fit. There is no better line than this which fits to this data. So then we use this line to explain the behavior of wages. And wages is our dependent variable, which means it is influenced by our education. So this is independent, this is dependent. This affects that. And this number here measures the size of the effect of x on y. In another video, we shall look at how to interpret this number, but for now, I wanted to illustrate how you calculate these two numbers. Once you have these two numbers, you have successfully fitted the OLS regression line. I hope you find this useful. The table itself illustrates that the fun we had with the summation sign, actually this is what it means when you are working with numbers. Sometimes some people struggle to understand when they see it written in symbols, but once you put it in numerical terms, they begin to understand. So I will stop here, then we will have another discussion on how to interpret these two numbers using economic theory.